Welcome to the third seminar for fall 2013 of chemistry. Today will be Kyle Burke, and he will let you know what he's talking about.
Okay, now the title of my study that I chose to do my presentation on is Photoelectron Spectroscopy and Theoretical Studies of Uranium Pentafluoride and Uranium Hexafluoride anions. Uranium hexafluoride is used, well, this has the presentation I have. I have an introduction. I'll be talking about the experimental methods, theoretical methods, results, and then I'll have a discussion about the conclusions, the introduction. Uranium hexafluoride is used in the refinement of uranium ore. It has 6 fluorines around it, and it is octahedral in its symmetry. An octahedron is bipyramidal. It has a square in the center, and it has an octahedron is defined as having 8 faces, which are all equilateral triangles. Uranium pentafluoride is a byproduct of the reactions that produce uranium hexafluoride. But there are many forms of uranium-containing compounds. It forms fluorides, chlorides, bromides, iodides, sulfides, nitrides, oxides, and probably a lot of other different compounds. Sulfates and phosphates, many different types of things can be formed with uranium. Uranium hexafluoride looks like salt, table salt, when it is just a solid, and it is easily gasified, liquefied, and stored as a solid. So therefore, it is of great use in the refinement of uranium. Now, the refinement of uranium is taking the uranium-238 isotopes and separating them from the uranium-235 isotopes. And this is done based on, I think it's centrifugation or they use these porous membranes which separate the smaller uranium-235 isotopes because they're smaller in their diameter, so they can be separated in this manner. And then it is gone through a series of different conversions from UF6 to UO2, and then it's made into fuel rods, where it is then put into reactors and then uses for energy. Now, photoelectron spectroscopy, or PES, is a method that's based on the photoelectric effect. Photoelectric effect is that any pure substance, originally it was studied on metals, pure metals, that when there's a light of high enough energy shining on a metal, then it will produce an electric current because that light will ionize some of the electrons. The electrons will have enough energy to escape. This is modeled by the equation. The kinetic energy of the electron that has been released, known as a photoelectron, is Planck's constant times the frequency of light minus the energy it requires to initially ionize those electrons, or initially remove the electrons from the metal. All the energies in this presentation are going to be recorded in electron volts. An electron volt is a very small quantity, 1.6 times 10 to the negative 19 joules, very small amount of energy. But when we're dealing with single atoms and molecules, it's enough to be useful. Now, for their apparatus that they're using, they refer to as a magnetic bottle PES apparatus, and it looks something like a combination of these two things here. The image on the left is known as a Paul trap, or a linear quadruple ion trap, where they use DC and AC electric fields to separate different ions. Now they separated their ions here because they produced both uranium hexafluoride anions and uranium pentafluoride anions. and they separate them in a very short amount of time, about only 0.1 seconds that they accrue in this ion trap. And this is, I think I pulled this off Google. It's just a very, they sell these things, but I'm sure that the contraption that they use looks something like this. There's very different types of, that's an older image of a PES apparatus. The experimental methods that were undergone. All right, the PES apparatus is basically a reaction chamber where they put depleted uranium-238 sulfate and silver fluoride, and they mix them together to, in acetonitrile, the substances react and produce uranium pentafluoride, uranium hexafluoride, just the neutral substances. Then they undergo ionization through a process called Electrospray Ionization, where they send a spray of electrons and by an electron spray source of some type, and they produce negative ions. And then they're carried along through the system by pulsing electric fields to the pole trap, which separates the ions, and then they're carried through a mass spectrometer, and then they are sent to a place where there's an ultraviolet laser, which is the place where they do the photoelectron spectroscopy, because the lasers will, by the photoelectric effect, excite photoelectrons from that substance. There were 3 different types of lasers that were used in the experiment. They used an F2 excimer laser, and it had the highest photon energy, which was 7.866 electron volts, and a very low ultraviolet. It's in the far ultraviolet region of 157 nanometers. They used a dye laser. There's several dye lasers which had wavelengths of 213, 245, and 275, which is slightly less energy, which actually gave them the best results in the photoelectron spectroscopy because they are of lesser energy. So there was more, there was higher resolution in those areas. And then they used a NDYAG laser, which is a 266 nanometer wavelength, which produces light of that wavelength. And this was the best resolution that they got from this laser, the third one, the NDYAG wavelength. Now this is the spectra of, because there was a mass spectrometer in this device, of the different substances that occurred. They found uranyl fluoride, which is basically the uranium fluoride compounds mixed with oxygen that were trapped in there was oxygen trapped in the apparatus. So then they had to flush it out with nitrogen gas, and then they got a better population of uranium hexafluoride and uranium pentafluoride anions. But these are the only 3 substances that were in large quantities anyways. Now these are I know this is a bad image because the way that it was in the text, I could have maybe spliced the image slightly differently, but you can't see the binding energy at the bottom, which is, there was a, what do you call it? Sorry. It's, can't think of it right now. It's basically the energy, the lowest energy can be seen about 3.8 electron volts to 5.2 electron volts is what is called the, well, anyways, it's just the range at which electrons are excited in this area. So this is the Frank-Condon factor best fitting to the 245 nanometer spectrum. they had to use the information from the 245 nanometer spectrum, because even though the 266 nanometer spectrum, which is the second to the top, it had the best resolution with the hot band transitions clearly visible. And those hot band transitions are the lines that are drawn vertically at the meeting at the peak of these transitions of the spectrum. But however, it's cut off in the highest energy level. So they had to use a 245 even though it had less resolution. Now, the entire purpose of this experiment was to obtain an electron affinity, or to determine the electron affinity from both uranium hexafluoride anions and uranium pentafluoride anions. This will tell us a lot of information about. Never mind, I said that. The electron affinity is defined as the energy change when a species is introduced, an extra electron is introduced into a chemical species, so that it goes from its neutral state to a negative state. So then with this, there are different vibrational energies that are, there are different geometry changes, different vibrational changes that occur because of the extra electron in that system. Now, ionization energy is somewhat the opposite of the electron affinity. It's what energy is it required in order to ionize a substance, in order to make an electron be removed from that system. So they are related, though, even though they're not exactly the same in the two equations I showed you, because the energy is on different sides of the excited electron. Now, what they used in this experiment to compare electron affinity to was the ADE, which is the adiabatic dissociation energy. The adiabatic dissociation energy is the minimum energy required to remove an electron from a molecule. Adiabatic is the term in physical chemistry used for no change of heat energy in a system. The vertical dissociation energy, or VDE, is the energy that is associated with when a species is excited. There may be excited by natural electron, rather. There may be geometry changes. There may be vibrational progressions and geometry changes that occur, and they're paired with vibrational transitions. And so the VDE is the energy of the transition from one vibrational state to a higher vibrational state upon ionization. In the experiments, they determined that these are previous experiments, sorry. In previous experiments, there were estimations of 4.0 plus or minus 0.4 electron volts, and for UF5, that's the electron affinity for UF5. That's what they're supposing that it should be, because it's transfer experiments between UF5 and an alkali atom. So alkali atoms are generally, they are, a single alkali atom is, it has a single electron in its valence structure, and it's very willing to release that electron so it can have a noble gas configuration. So this charge transfer experiment could give an accurate result, an accurate electron affinity value. Now, for uranium hexafluoride, the charge transfer experiment yielded an electron volt of 5.1. It should be greater than or equal to 5.1 electron volts. Charge transfer reaction between uranium hexafluoride anion and boron trifluoride gives an estimate of 4.9 plus or minus 0.5 electron volts for UF6. Notice that 4.9 and 5.1 are very similar electron affinities for UF6. Let's see, for ion equilibrium studies, 3.7 plus or minus 0.2 electron volts and 5.1 plus or minus 0.2 electron volts for uranium pentafluoride and uranium hexafluoride respectively were suggested as the electron affinities. And these previous studies were used to determine the accuracy of the theoretical methods and the experimental methods and the values of the electron affinities that were obtained. Theoretical methods that were used in this study. Computations performed in the theoretical analysis of UF6 negative and UF5 negative were done on a computer known as the DCOMP 7000 at the Supercomputer Center of the Computer Network Information Center at the Chinese Academy of Sciences, and also at the Shanghai Computing Center. This was a joint effort by the United States and the U.S., or the United States and China. Portion of the computations were done at the EMSL, which stands for the Environmental Molecular Sciences Laboratory, which is sponsored by the U.S. Department of Energy. And this is, of course, of great concern to the United States Department of Energy because this is how we obtain much of our energy from nuclear fuel. So there were two different types of theoretic calculations done in this experiment, in the theoretical experimentation of this study. There were ab initio wave function theory and density functional theory. Ab initio wave function theory uses wave functions which are based on the vibration of well, originally they came from the vibrations of a violin string, things of this nature. They obtain chemical and physical properties. They determine chemical and physical properties of substances using solutions. They obtain a solution to the wave function, which is really very difficult mathematics. They have very large basis sets, we call them, which is all the information that we put into the computer, which determines all the relativistic effects of the electron, repulsion, coupling energies that occur in a many electron system. The specific wave function theory method used by the researchers is the coupled cluster with singles, doubles, and perturbative triples. They also used a coupled cluster, singles, triples, and perturbative doubles method. They used a density functional method, and now a density functional method is using functionals, which functionals are where you take a function such as the electron densities and you put them into another function. The particular function that they used was a Purdue Burke-Earnserhoff or PBE exchange correlation functional, which I believe they actually did their own writing of code for this, which was, these researchers have actually done many different other experiments. I don't know of any of them offhand, but I did look up that they are active researchers. So they used another type of computer programming to that has been shown accuracy in computations involving uranyl and neptunal compounds. So they thought that this method would obtain accurate results because it has already been used before on similar compounds. Experimental results. Uranium hexafluoride anions. No photoelectrons were detectable at any of the photon energies available, even the highest photon energy available to the researchers using the F2 X-ray laser, which had 7.866 electron volts per photon. And this is surprising because of all the previous research, like the bits of material that were discussed earlier about the charge transfer reactions, ionic equilibrium studies were suggested that the detachment energy of electrons, if UF6 negative, should be around 5.1 or something like that, but at least should be less than 6 electron volts. So this was inconclusive. Now the uranium pentafluoride anion, the PES spectra were only obtainable at 4 energy levels. There was actually a 5th one, but they didn't find any other differentiation in the transitions, in the hot band transitions, or in the resolution of the peaks. And that was the F2 laser, which had the highest energy. So at these energies, the 213 nanometer, 245, 266, and 275 nanometers, they had the best resolution, because the other ones were either too much energy or too little energy to get results which were useful. There was a wide detachment band at the 213 nanometer level, which was between 3.8 and 5.2 electron volts, and now and that represents the binding energy. Binding energy is a measure of how well a substance is held together, and what energies are required to make it dissociate into smaller parts. There is a large geometric change between neutral uranium hexafluoride and its excited state. The 266 nanometer spectrum is the best resolution and shows the hot band transitions between vibrationally excited states. However, the far right, or the higher energy, binding energy part of the spectrum is cut off because there's lower energy in the 266 nanometers and 245 nanometers. 245 nanometers is more continuous, the spectrum of that. And if I could, I'm going to go and show that again. Let me see. Yes, spectra. Here, nope. There we go. You see how the 245 is more, it's continuous, whereas the top two are discontinuous because of the lower energy 266 nanometers, the nanometers. As the wavelength is bigger, there's less energy, and so in the higher part of the binding energy, there was no photoelectrons that could be emitted because there's not enough energy in those wavelengths. So let me get back to the other slide. All right, oops. Okay. Now the 245 nanometer spectrum was used to compare with an FCF Frank-Condon factor simulation. Now, we never talked about Frank-Condon factor in even physical chemistry, so I can't really tell you much about it. It's based on something called the Frank-Condon principle, and that has to do with the transitions between different vibrational and electronic states, which is what we're talking about here. You're exciting electrons and trying to get them to release, or trying to add another electron into a system. Now, and the spectrum that was the Frank-Condon factor, it was based on the 245 nanometer, and it suggests that the electron affinity is about 3.8 plus or minus 0.05 electron volts. Theoretic results. Uranium hexafluoride anion. UF6 and its anion are found to have highly symmetric octahedral symmetry point group. Calculated bond lengths from density functional theory of PBE and CCSDT are 2.1 angstroms and 2.02 angstroms, respectively. There's a lot of difference in the two different levels of theory that they use. But however, these are very similar bond lengths, 2.1 angstroms and 2.02, and they're using it on the same species here, but they are producing different results based on the level of theory and their pros and cons to using either one of them. The adiabatic dissociation energy calculated by the DFT-PV was 4.06 electron volts, and by the CCSDT method was 5.20 electron volts. And you can see there's a great difference between those of about 1.1 electron volts, which is a huge difference. If we're, I mean, it really is a large difference between the two. The VDE calculated by the density functional theory was 4.43 electron volts, and by CCSDT was 5.72, which again is a very large difference, 1.3. So uranium pentafluoride anion. Neutral uranium pentafluoride shows a significantly shorter UF bond length in both ground and excited states than UF5 negative, which suggests that UF5 negative has a lower binding energy than UF6 or UF5 neutral, because if you add an extra electron into a species that's perfectly happy without that extra electron, then it might go into, the electron is likely to go into an anti-bonding orbital, where it would increase the energy, the total energy of the system, making it less stable. So it would make sense that it has a larger bond length, UF bond length on average, than the neutral UF5 without the extra electron. Now both methods, the CCSDT and the DFT method, give similar values for the bond length. They used two different levels of the wave function theory. They used one using scalar relativistic effects, or SR, and one using spin orbital coupling effects, which gave almost identical adiabatic dissociation energies and vertical dissociation energies. 2.63 for the adiabatic dissociation energy and 3.13 electron volts. But those are significantly lower than the coupled cluster. Oh, I'm sorry, I think I said that wrong earlier, that the DFT method gave 2.63 electron volts and 3.13 electron volts for the adiabatic dissociation energy and the vertical dissociation energy, respectively. And they are also significantly lower by about 1 electron volt than the decoupled cluster method, which is 4.48 and 4.20 electron volts for the adiabatic, for the ADE and for the VDE values, respectively. However, both levels of theory give similar F axial, fluorine axial, uranium, fluorine equilateral bond. Now the axial is the bond that goes like this, and then the equilateral is the one that goes off like this. So that they give similar bond angles is a good sign of that they have the geometry best described. The geometry, both in uranium hexafluoride and uranium hexafluoride anion, are both found to be octahedral, and the geometry in uranium pentafluoride and uranium pentafluoride anion are both found to be C4b, which is a square with it's a square pyramid, like the pyramids at Giza. They also calculated symmetric frequencies for the totally symmetric uranium fluoride bond vibrational mode, and it's in good agreement with that derived from an experiment, which is about 650 per centimeter, which they used to then fit with the Frank Condon factor simulation. Let's see, continuing on. And I've already gone through these data, but they found that there was a systematic error in these calculations of about 0.34 for the adiabatic dissociation energy. They were basically, as I was saying, I was bringing up the relationship between ADE, or adiabatic dissociation energy, and the electron affinity, which they basically compared the two as one and the same in this experiment, even though there's a correctional factor, I guess, of 0.34 electron volts. So the experimental values here are compared with the theoretical values. Now, the experimental value for the adiabatic dissociation energy, or ADE, is 3.82, around there, plus or minus 0.05 electron volts, which is the coupled cluster with singles, doubles, and triples was 3.48, which is just lower than that by about 0.3. And then the VDE is 4.20, which and that's the coupled cluster calculation. 4.4 is about 0.2 electron volts away from there. But really, the vertical dissociation energy wasn't used in the calculation of the electron affinity. This is continue. Oh, also that was for uranium pentafluoride. Now for uranium hexafluoride, the coupled cluster is 5.2. They had no experimental data to compare it to, because they didn't elicit photoelectrons from the photoelectron spectroscopy. So, but actually the same coupled cluster systematic error arose with about 0.34, and if you add 0.34 to that, it's about 5.5, which is in good agreement with previous experiments that it should be above 5 electron volts, and less than 6. So it's right in the middle, and it seems reasonable. These are the geometrical parameters that were both calculated and were used in other calculations, like the Frank Condon factor simulation. The uranium fluoride axial length and uranium pentafluoride anion is about 2.13, and the neutral uranium pentafluoride is about 2.03. So the increase in bond length means that it's less stable, that there's more energy in the system. So and in the uranium hexafluoride anion, it's a greater bond length, about by 0.8 or so, 0.6, 0.7 maybe, from the neutral uranium hexafluoride species. The stretching, the vibrational, what's it called? The frequency of the vibration was 534 per centimeter. I really have never known what per centimeter is, but I guess that's what it is. I'm sorry, I can't go any further into this. I'm not at the graduate level. The two methods, coupled clusters and DFT, calculate about the same length for both the UF6 negative and UF5 negative for their bond lengths, but there is a different, there's a slightly different, each one of these uranium, bond angles are lower than the ones over here, so they underestimate the bond angle. Bond angle, well, actually not just the bond angle, but most of the DFT calculations were underestimations than the couple cluster, which seemed to be more better at calculating for this particular molecule. And these are the calculated, well, these are the parameters that were used for the Frank-Condon factor. They were similar to the 650 nanometers, which was, or 650 per centimeter vibrational frequency, which was determined from the PES spectra of UF5. And these are all for UF5. These are all the determination of the electron affinity for UF5, which is about 3.82, which that came directly from the Frank-Condon factor analysis, which is in good agreement with all the previous research that was done. And now these are the energy levels generated by the computations for uranium hexafluoride, uranium pentafluoride anion. They didn't have any of this in the on uranium hexafluoride though, for some reason. But they say that the two highest electrons, there is one electron in the 2b2, which is the first red one, the lowest red. It's an antibody orbital along with the 8A1. There are two electrons in this, and they're said that because of the detachment cross section, it's very small in the 8A1 molecular orbital as opposed to the 2B2 molecular orbital, about 10 times weaker in the 8A1. And this is why they say that there were no photoelectrons that were released upon the photoelectron spectroscopy of UF6. Now these are some of the generated iso surfaces of the isopotential energy surfaces of the uranium pentafluoride anions. And it can be seen in the 6A1 and 5A1 that it's clearly, and also 7A1 as well. These three, it's clearly C4V, or the square pyramidal symmetry discussion. As I said earlier, the coupled cluster calculations for the adiabatic dissociation energy is most consistent with the experiment, and the density functional theory calculations greatly underestimated the electron detachment energies. Although, as I said, the experimental values of the coupled cluster method is lower by 0.34 electron volts. They actually determined this using other research that they had done, that their methods on similar compounds were going to be off by a systematic error of about this much, 0.34. So the estimated electron affinities of uranium hexafluoride anion is about 3.8, and their estimated electron affinity for uranium, oh sorry, I said that wrong. UF5 negative is about 3.8, and UF6 is 5.5 electron volts. That's what they determined at the end of it. Now, the reason that they wanted to determine the electron affinities, my guess is, well, any little bit of information that you can get about theoretical physics or chemistry is very essential if you're dealing with reactions with these things. Maybe the stability of uranium hexafluoride anions are of importance, because I actually found in the document they were talking about a cesium plus uranium hexafluoride anion crystal, So maybe there's different ways that you can store it, or I don't know, it may have different electrical properties. It could be, I don't know, conductive to electricity or something like this. More soluble. I don't really have any idea why they would want to know the electron affinity. But maybe one day, these computations similar to this and experiments similar to this, maybe one day actinide chemistry can be as complete as, say, organic chemistry. I mean, as I said earlier in the presentation, uranium forms many different compounds, just like carbon forms many different compounds. And perhaps you can form really long chains, just like carbon. Maybe not, but it's speculation. But that's my presentation. Any questions?
I have a couple questions. Some kind of basic questions and then some more theoretical ones. When you first started talking about it, you were talking about the centrifugation of these compounds and why it's important, how it works. I guess probably, I don't know if you guys, audience members, recognize that this is a big deal in the news because of the fact that Iran is trying to make centrifuges that would be powerful enough to separate the different isotopes of uranium. So when you were talking about how the centrifuge separates them, you said something about size. Do you think it's really by size?
Oh, maybe, sorry, by mass then. I don't know if it's actually centrifugation, but I've heard of two different ways. I think one is the centrifugation method, and another is using some membrane that has, because of the size of those, the diameter of those, that they're able to pass through the membrane.
Okay, it's not really the size. Size has nothing to do with it because isotopes are essentially the same. Are you talking about the nucleus, and we're talking about molecules in which the nucleus is
Sorry,
tiny.
about that.
So it's really all by mass.
Okay, well then that would make sense that it's all just done by centrifugation. Yeah.
Well, it's done by centrifugation, which separates them by mass. And then the other one, you're talking about the membrane, that's also by mass because if it's heavier, it's traveling a little bit slower. So less of it goes through the hole in the membrane if it's heavier. But you're talking about tiny differences in mass, right?
Certainly.
So it's a huge deal to try to get these things separated from each other. That's why you have to have these gigantic centrifuges and all that kind of stuff.
Very costly.
Right, but anyway, you all recognize hopefully that the only difference between uranium hexafluoride with uranium what are the numbers? 238 versus 235. It's 3 mass units between these molecules that are probably molar masses of hundreds. So it's very different, very small difference in mass. But anyway, that brings up the next question, which was in the slide where you were talking about calculating the electron affinities. You had something about by charge transfer method. Put that slide back up.
Charge transfer?
Right, that's the one. Yep. Well, I have 2 questions about that. First of all, how did they measure the energies of these charge transfer? Essentially what you're talking about is the UF6 negative is transferring an electron to something else, or something else is transferring an electron to UF6. It's becoming UF6 negative. So we're talking about the difference between UF6 versus UF6 negative. So it's transferring an electron. And you say an estimated value of about 5 electron volts for UF6.
Where are you reading?
This second major sentence, charge transfer reaction between UF6 negative and BF3 gives an estimated essentially 5 electron volts. Do you have any idea how they measured that?
I really have no idea, and they didn't say in the experiment.
Okay.
I guess I can speculate if you want me to do it. But,
Sure, speculate.
well, let's see. I really can't tell you. I'm sorry.
Well,
Is that really, when they're saying between the UF6 minus and BF3, but then after it says for UF6, so what were the actual compounds with the transfer? It seems inconclusive in that sentence as to what the reaction really was.
Well, I don't know, maybe boron is more willing to accept the electron.
What was being started with and ended with?
Well, I'm sorry, I don't understand your question.
It says charge transfer between UF6 minus and BF3. That makes me think there's a UF6 minus and a BF3, and they're passing electrons.
Right.
But then after it says gives an estimate of the energy for UF6. Well, that's not UF6, it's UF6 minus. So is that a typo? Is there a
the electrons,
difference? I don't
I
understand
think
how.
that's exactly how it is. But if you want me to look it up right here,
You see what I'm saying?
I know exactly, and that was going to be my next question.
Here we go. Yeah, it's exactly what they say. Charge transfer reaction between UF6 negative and BF3 yields an EA of about 4.9 for UF6.
So how could that be? There's a way that they can determine what the electron affinity for UF6 is by measuring the energy of the reaction between UF6 negative and BF3.
And as I already said earlier, there is a relationship between the ionization energy and electron affinity. They're really just the reverse equation almost.
Exactly. So if you know the energy it requires for UF6 negative to give an electron to BF3,
Then you know
it's
the
just the
same
negative
energy.
of the energy vector, right?
However, I don't think that they are exactly the same because, I mean, there might be small differences between ionization energy and electron affinity, even though they are reversed, but
You're absolutely right.
there's maybe...
So what is the difference?
Well,
Why does it work here, but it's not depending upon exactly saying that the two things are the same as each other?
Nothing's coming to me right now, I'm afraid.
Well, it's really just all a matter of how you define things. But I have another question here. One little word that I think might have been wrong on one of your slides, you talked about a neutral UF6 negative as compared to the excited.
As opposed to an excited state.
Right. It seems how can you have something that's negative but be neutral?
Well, it's in its lowest energy state.
Okay, so
And
you don't really
we're doing
mean-
other calculations with higher energy states.
So you don't really mean neutral?
No, I don't. Well, I mean the lowest energy state of that extra electron species.
And what's that called? There's a word for the lowest energy state.
Ground state
There
or
you go.
UF.
Ground state, that's what you meant. You didn't mean
Sorry,
neutral.
yeah.
Yeah.
But they were doing other research in this experiment for the second transition, the second electron feed released, and that might be one reason that they were using the word neutral as opposed to excited.
So they used the word neutral? Okay. I think that's a misstatement, but I could be not under, because it seems to me the word neutral
I've
applied
actually
to
found
something that's negative.
Some typos in here.
Absolutely, it happens all the time. You'd be surprised how often typos occur in these papers. Okay, I have a couple other questions, but I'll let other people.
I'm going to have a really, really simple question. You talked about there was a systematic error that was built into the system, and you said it was at 0.34 electron volts. What if they had recognized a proportional error? What would you expect to have found instead of a systematic error? What if the error had been proportional?
Well, then they wouldn't have, they were just adding the 0.34 volts, but if it was proportional, then isn't that a multiplicative scalar being multiplied by?
So as the differences became greater,
Right, as the difference begins, then it becomes a greater change in error. However, the relationship between the two levels of theory, the density functional theory and the wave function method, they were both scalarly additively proportionate, I guess, as opposed to like multiplying a constant, which if you get to greater and greater levels, then there would be a greater and greater error, right?
Right.
But I think it's all based on their previous research that they had found this out because of their methods. Did I
That's
answer your question?
good as I
Good as
can
you
get.
All
Yeah.
right, I have one breakout. You mentioned somewhere that there was, on one of the bands was from 3.8 to 5.2 electron volts, and that suggested a large geometric change. Could you explain why that suggests a large geometric change?
Honestly, it's just, I'm going on based on what the researchers were saying. I don't fully.
Think about it.
Okay.
If in a wide band like that, why would that suggest a large geometric change?
So at 3.8, electrons start getting excited, and then at 5.2 they stop being excited. I guess it's more than enough energy required.
Okay. If there wasn't a large change, what would you expect?
Smaller detachment energy.
Smaller
yes.
energy?
Well, no, a band of
Why?
attachment band. Because then perhaps as the geometry, if it stays the same, then it'll be only a narrow range that you'll see on the spectrum, like
Why?
a single spectrum.
You're exactly right. I'm trying to get you to dig into why that happens.
Because of the vibrational progression, maybe there's different geometry changes, and then because of those different geometry changes, there's different energy levels, and then I don't know. I'm just following the pieces here. Sorry.
As geometry changes more, there are more choices of energy levels for the electrons to transfer to. So you get small variations where this might be 3.8, but if this changes a little bit, it might go up a little. Now it's 3.9. If this goes way out here, maybe it goes up to 5.2. The more change there is, the more variation there is in the allowed excitations, because there's more choices. And those choices aren't all the same energy. That make sense?
Yeah, I think I knew that. I just can't really put it into words, and I'm sorry.
Okay.
We're past out of time.
Yeah, we're pretty much out.
Thank you, Kyle. By the way, that reciprocal centimeter thing, the centimeters to the -1, that's just the inverse of the wavelength.
Oh, okay. So 1 divided by
Called the wave number.
It's called a wave number. And it's kind of out of fashion anymore, but they use it because it's proportional to the energy, whereas wavelength is inversely proportional to the energy.
So if people are afraid of inverse proportions, they just made it up as something to talk about.
To me, always, I think it's frequency based. It's just proportional.
Just a different unit.
Right.
Just a converter.
Same thing, but then